But what? So what have I got? I've got y dot y t args h0. So the thing I'm missing is passing. So odeint is just calculating one step, and my loop is here. So what I'm going to do is put this loop, which generates all the solutions or steps through the solution. That loop is going into my ODE integrator. Okay. So previously this function only, or at the moment it's only calculating one step, but it's actually going to do all the steps. So I'm going to pass it an object which is my t array, and my t array is going to be, in this case, it's going to be a linspace of starting from time start, ending at time end, and it's going to have number of steps as steps. Okay. So there's my time array, and now this loop is going to go into my ODE integrator. So I'm going to somehow wrap this around it. Okay. So I'm saying it's going through all the steps in the T array. So for x in I range number of steps, find the derivative. So let's say, let's go back to this notation, x current equals x, and I'm going to clone that, make sure it's a copy of x, not the actual list, so if I change any values here it doesn't update the thing that I've passed. And x next, so I'm going to change all those to x current, current. So remember I changed my t here to have t, and I'd call my step size h0 because that's what it's called in Python's inbuilt one. So look, let's just say step size equals h0, so the height of the step. Right, how have I done? So this time I'm going to say number of steps is actually the length of t. So in this situation, assume t is incremented in steps of size, step size. So this isn't always true for different methods, but we'll say here. So t is incremented, so so for I in range t, so the number of time steps is the length of my time array. Then the initial time is t0, so t, let's call this ti. And in general, when we call the derivative function, we allow ourselves to set the time as a parameter as well. So I'm going to pass that as a time and just reflect that up here. T. So although I set it here, I'm not actually going to call it because in this model there's no time dependence of the rates, sort of explicit time dependence, so it just depends on the volume. So ti. So this is saying step through all the time steps. Then we can say the time at this step. So ti equals ti. Okay. And as long as I've set up this array so it's incremented in time steps, this will be true. So x next at time I is this. So that should work. And then down here, get derivatives. I'm just going to make sure when I call x dot here, I've passed it the ti as well. Okay, I've done that. So here is my code. So in this loop here, I load in my initial conditions. So now, because x isn't just at one step, it's the initial conditions I'm passing. Let's call that x0 there and there. So the current is the initial condition, and then I'm going to loop through all the time steps. But instead of returning just the value for one step, I'm going to need to store all the results into a vector. So for this, let's do the same thing again. So let's say results equals, and here, so that's an empty list. So for every time I increment one time step, I'm going to load it into my results. So results dot append x next. So then I'll say x current equals x next. And again, just to be careful, you know, I could say, do I want to copy this object so it doesn't, so whatever I do doesn't overwrite it, or does it matter? And in this case, I can just have one list which I continually update, so I could get away without taking a copy. But in general, you take a slight performance hit if you're constantly copying this, but if you're not sure whether it's going to cause you problems, if you take a copy, then you know it's not going to cause you problems. So for instance here, I said results append x next. So then if I then try and work with x next, it's still saved in this results. So logically, what I think I'd do is store a copy of x next in my results thing, and then I know whatever I do afterwards isn't going to change the thing in the results. So this is all dealt with in the working with objects, where we talk about whether objects are mutable or immutable. Okay, so if you're not sure what I'm talking about and why I'm copying this list, have a look at that and hopefully it will make sense. So we've got x current equals x next return, and then I'm going to return the results. Okay, so I'm returning a list of, for each time step, I'm putting in the x values for each time step, and just to begin with, I need to load up the results. So I need to say results dot append x current, and again I'm going to put a copy in, so if I ever change these, it doesn't change the thing I've stored into my results. Right, so now I've got something that looks like the ODE integrator that Python provides. So let me just adjust what I'm doing here. So now I'm going to say, remember the results are the same thing as this recorded x, and hopefully when I run this, the changes I've made will all be fine. So let's see what happens. So